put the citation for the paper here because it's not in the Proceedings of Learning at Scale, if anyone cares to check it. And in this talk, I'll discuss some work where we propose a method for measuring the fairness of predictive models, and then we'll demonstrate the results of this method when applied to dropout prediction in MOOCs. And at a high level, our results really suggest that fairness in MOOC dropout prediction, at least, is something that we should be paying more attention to, and also that we can improve the fairness of our models without necessarily sacrificing performance in practice. This work really takes inspiration from Ali Rahimi's Test of Time award acceptance speech at NeurIPS in 2017. I would encourage you to take a look at that video. But in it, he suggests that the field of machine learning is performing alchemy by pushing for predictive advances without a clear understanding of the theory or implications behind what's driving these improvements in accuracy or classification performance. And in a follow-up paper with D. Scully et al., they go further and they suggest that this winning above all else mentality has been driving the field of machine learning, and that it's beset by what they call a winner's curse, where predictive performance is prioritized above deeply understanding predictive models and their effects. And I think there's really a kernel of truth to this idea that probably resonates with many folks who are kind of consumers of machine learning research or even producers of it. And in the field of education, this winning over everything mindset can have genuine practical consequences, as we'll show. And I really think that our field has a responsibility to investigate, understand, and minimize unfairness in predictive models to the extent that that's possible. Because we definitely don't want to find ourselves in the position of not fully understanding our models. I think that it can have even greater implications than something like an image classification model. And there's certainly more to our work than just winning, as these authors might put it. So obviously, there's at this point, a very high degree of awareness that many machine learning and AI methods are not only unbiased, not unbiased in many deployments, but they can actually learn and reinforce existing injustices. I'm not going to go through the research here, but one thing that I do want to point out that's particularly interesting is there's a growing body of evidence that existing predictive algorithms in some cases have similar discriminatory effects to their non-algorithmic historical predecessors. So on the right here is a graphic and a link to a study that shows how a predictive credit model, which gives loans for real estate, actually sort of mimics the patterns of a redlining model or map, which was explicitly designed to discriminate, almost 75 years before this new algorithmic model was deployed. So I think there's an agreement that this is an important issue and that it affects machine learning models in a variety of different applications. And correcting, unfair or potentially discriminatory predictive models has been an active research area over the past, especially over the past 5 years, but going back even further. And in a nice survey work, Corbett, Davies, and Gohl identify kind of 3 main areas of prior work. And the first they call anti-classification, where we might remove the protected attribute from an input data set. So if we want to be fair with respect to age or gender, we might just not provide that to a prediction model. Unfortunately, as we'll show, that really doesn't help very much because other correlations in the data set can still be used to learn models which can display the same types of unfairness. Classification parity is a general family of approaches where we try to make equitable predictions at a group level. So we want the group-wise statistics to look the same across protected attribute groups. And a third broad approach to fairness that they describe is calibration, where we try to make our predictions independent of the protected attribute, conditional on risk estimates. And I provide some citations there for interested readers to read a bit more about these. But each of these kind of, we argue, is really not adequate for the types of predictive models that are often used in education, and especially for MOOC dropout prediction, which this study focuses on. The first, as I mentioned, is really insufficient to guarantee fairness. Classification parity actually can require unfair individual classifications in order to equalize the statistics across groups. So we might, even if we say had strong reason to think that an individual would drop out, we might predict that they wouldn't in order to equalize the statistics with another group, demographic group. And calibration only applies to one prediction threshold. So you choose a probability at which you would, predict that a student is going to drop out, and you evaluate the calibration at that specific probability threshold. But as we'll argue later, we really need evaluation methods for fairness in educational models, which can evaluate the full range of possible thresholds, all the way from 0 to 1. And so the method that we'll propose is really designed to meet these, to address these shortcomings. So I'm really going to focus here on the methodology. We did do an experiment, and hopefully I have time to get to that. But I think the most important thing that I hope to kind of be able to discuss for this audience is the approach at a high level that we kind of lay out in this work. So the Scully and Rahimi paper that I mentioned previously proposes this idea, which they call slicing analysis, in order to better understand the alchemy of modern statistical models. And slicing analysis is just the process of evaluating model performance across different dimensions or subgroups of a data set. These are called different slices, in order to gain a more nuanced understanding of model performance across subgroups. And I actually think both of the previous talks in this session showed some good examples of that. But we're specifically talking about this in the context of machine learning models and prediction models. And so prior to Scully's work, there had been very little research which had taken up the call for slicing analysis in machine learning broadly, or in learning analytics in particular. But I think since then, there has been an encouraging uptick in this kind of work, even since this paper was presented about a year ago. But I think it's also important that the Scully paper leaves open the question of how to perform these analyses. There's no widely accepted formal methodology for conducting slicing analyses even now. And so one thing we try to do in our work is set forth an approach for doing that in one prediction context. So I think there are several reasons that this type of analysis will be motivated. I won't go into them in too much detail here, but I do want to say that I think this work is only more urgent now that we've seen this kind of near complete transition of educational models to online learning across the globe, and an increased rollout of predictive models to do things like at-risk student prediction. So many of these motivations are discussed in our paper, but I will refer you to there. In this work, the way that we define fairness is with respect to equalized performance across different subgroups of a sensitive attribute. So this is the definition of fairness that we operate on in this work, that a model is fair with respect to that attribute if it achieves similar performance across all subgroups of the demographic attribute, be that age or gender or nationality. This also means that the subgroups should benefit equally from the predictions of a model when it's deployed, because it will work equally well for all of the groups. This is very different from the fairness definitions that often get used in work where they're trying to predict things like loans or recidivism in the machine learning literature, because their one outcome is clearly better than the others. But in the case of an at-risk prediction, we actually just want to get it right so that we can get students what they need. And so the method we propose for conducting slicing analysis relies on the area under the receiver operating characteristic curve. This is a metric that's commonly used to evaluate especially binary classification models. It plots the true positive and false positive rates for the model across all possible classification thresholds from 0 to 1. And a curve that goes higher and to the left is better. So we want models that have high true positive rates, even when the prediction threshold is low. And evaluating models across all possible thresholds is particularly important for educational models, because our interventions in education might range, or we might use interventions that are based on a range of possible thresholds from just one predictive model. So as an example, so yeah, this shows all the different thresholds. In an example, we might use a low threshold for something like an email intervention where we send an automated reminder for a student to return to the course. Might send that to everyone with a low predicted probability of dropping out. But for more kind of resource intensive interventions, such as using a human tutor or having an instructor have one-on-one time with a student, we'd use a much higher threshold. So it matters if our model performs well across all different thresholds, because one trained model might be used to power several different interventions. And so our field really needs a procedure for evaluating our models across all possible thresholds, not just at one point on this curve, which is what something like equalized odds would do. And so the procedure that we propose is shown on the right here visually. These are actually, so the first two plots are example ROC curves for two example groups. Here they're male and female in a MOOC based on a predictive model. And the plot on the right shows our proposed method, which essentially takes the integral between these two curves. We call this the absolute between ROC area, or ABROCA. So the mathematical formulation of the ABROCA is here. Like I said, it's just an integral over the two curves. It takes the absolute distance between them, or the area between them. I think it's important to note, actually, so let's take a look at a detailed example here, just given the time. The slice plot alone allows us to gather a lot of rich information about the model performance, much more than something like equalized odds alone would allow us to do. So for example, in the image shown here, which is for one of the MOOCs that we evaluated in our study, we can see that there are points where equalized odds is achieved. So if we measured it at those points, we would say this model is fair according to that criterion. But we can also see there are several other thresholds at which there are significant differences in the performance. And indeed, large divergences kind of in the middle and the lower range, which is where we might most often deploy an intervention using such a dropout prediction model in a MOOC. And so the ABROCA statistic measures that entire area. And we could also adjust the limits of integration if we thought we only cared about certain regions, or we would only use certain thresholds for an intervention based on this. So this is our proposed method for conducting slicing analyses. You could easily do this across multiple demographic groups as well, not just two groups, by using a reference curve. So one group as kind of the majority group and comparing all other groups to that one. So I'll just briefly mention that we did an experiment with this across a large set of 45 MOOCs. We looked at several different prediction models from prior work. Including some of our own prior work, because it was a replication study. We replicated some of our work and some others. We found that there were significant differences kind of across the board. The experimental details are in the paper, but what I think is particularly interesting, kind of two things. We found a clear relationship between the gender balance in the course and the model unfairness measured by the ABROCA. So courses which deviated significantly from the average gender ratio, we saw higher ABROCAs, which equates to, under our definition, larger unfairness. And I think this is kind of the most important finding in my mind, is that we don't see a clear trade-off between the model performance and the model's unfairness. So they're not very strongly correlated. And it's possible to have a model which has a high AUC, which is a good performance measure, and also a low ABROCA. But it's also possible kind of to have different combinations of that, so poor performance and unfairness, for example. So I think these provide further impetus for the use of slicing analysis to support learning analytics models. If we can improve our models' fairness without really sacrificing their performance in practice, and maybe also thorough model evaluation can help to improve our models by comparing others which could achieve better performance. But I think really this is kind of the beginning of this type of analysis in the rich literature on prediction in MOOCs, and hopefully folks take up this call and we see this more in future studies like we've started to do. So I just want to be conscientious of time. And so I think with that, maybe I'll wrap up.
Great. Thank you, Josh.
Yeah.
For this Fantastic presentation. I encourage everybody to check out the paper. I found it very thought-provoking myself, and inspired our research group to do some more work into fairness as well.
Yeah.
Well done on moving our field into that direction.